Right, great. Hi everyone again. Again, my name is Husam, Alissa. I'm Director of the Systems Technology team and Microsoft Cloud Operation Innovation. Today we will share a lifecycle assessment analysis and study that we've ran in which we were quantifying the impact of advanced cooling solutions from a sustainability, obviously from a sustainability point of view. And as the title shows, we'll be comparing the impact of different what-if scenarios where we have the benchmark be air cooling, and then we'll be looking at some advanced cooling techs, cold plates, single-phase immersion, and two-phase immersion as well. So our agenda for today, we'll give you some background kind of on the thought process on the study and how we started it. And then we'll do a quick recap on the different technologies that we'll be looking at. Then we'll walk through the LCA definitions, methodology, terminology, and we'll go through the results. I also want to highlight that we will be sharing, so when we did this lifecycle assessment work, we actually, one of the outcome was a tool to run lifecycle assessment for cooling techs. Which we will be working with a sustainability workstream to contribute to OCP, so end users and cooling technology vendors can actually use it to look at the sustainability impact of their techs. Now, just a quick recap. As you can see in this slide, the data center industry, hyperscalers, and Microsoft have been on a long journey of optimizing data center PUE. As you can see, those are air-cooled data centers, and you can see that we're going to PUEs as low as 1.1. So it's been a journey of optimization, lowering that energy overhead, maximizing the energy efficiency of the data center. But as we all know, we're moving to more liquid cooling territory. Now, as was mentioned through the talks today and yesterday, for air-cooled sites, we look at liquid-to-air enablement solutions like Sidekick. But our focus today is going to be on an analysis where we'll be looking at a hypothetical liquid-cooled data center that is equipped with warm facility cooling loop. That warm facility cooling loop will be supporting the different liquid cooling technologies such as cold plates, single-phase immersion, as well as two-phase immersion. Well, a couple of disclaimers here. For any of these three techs we're showing here, there is room for optimization and improvement, but that is not a thing that we're going to visit in this study. We're basically going to look at the main applications of these techs from a life cycle assessment point of view. And again, this is another reason why we're going to be contributing the tool to OCP, so different liquid cooling vendors can assess their technologies with their specific set of optimizations. Another thing is, it's important here, one thing we emphasize in this work is the systems thinking again. I know I've been saying this today multiple times, but if you think about it, we're introducing a cooling technology X, whatever it is. It'll have an impact to the chip. You could call it overclocking, performance boost, velocity boosting, extended turbo, whatever it is. The software could take advantage of that. And then just moving to the hardware and the server, there will be an impact to the server power consumption. And then going to the data center itself, the infrastructure to support that cooling technology, those decisions will impact the data center PUE, and hence will impact what we're getting from the utility and what's being converted into IT capacity. So what I'm trying to convey here is that single cooling technology decision really affects the whole stack. And this is what we're going to be covering in this LCA. This is an LCA that covers the software, the chip, the server, the facility, and also the grid decision when we go with any of these cooling techs. We're going to be baselining against air cooling, and then we'll be comparing with the different cooling technologies that we're showing here. And all right.
Sorry.
Good, no worries. All right, and with that, I'll hand it over to Julie.
Yeah. Is this on? Yes?
Yeah, let me just make sure.
One more. There we go. Hello, everyone. I'm Julie Sinistore. I'm from WSP. And I'm really grateful, actually, that the last speaker went over scope 1, 2, and 3, because now you're going to get a crash course in LCA. Quick show of hands. Does anyone already know what LCA is? Okay, strong amount. Crash course reminder for those of you, maybe this is a brand new topic, but life cycle assessment is a systematic way of evaluating the environmental impacts from all of the life cycle phases of a product or a service. So it's not just the data center, but it's actually the service of provisioning the product to the customer, like virtual machines, virtual cores, et cetera. So in life cycle assessment, we take into account everything from cradle to grave. That includes raw material extraction of resources. Commonly, when we think about resources, we think about what I have pictured here, which is a pit in a mine, and we're taking things out of the ground. But I just like to remind people, you extract resources not just from the ground, but actually also from the air and the water. Those resources go into the product system. They're transformed into intermediate products. So think raw ore is turned into iron, is turned into rebar, or other types of steel products is turned into a building, et cetera. We take all of that into account, including the transportation steps in between. We take into account the use of the product. So that would be the energy that's used in the life cycle use phase of the product. We take into account operational maintenance, any kinds of other inputs that have to go in the case of a data center, also replacing equipment as it wears out or is upgraded. We also take into account the end of life. We hope, as with some of the earlier presentations, it gets recycled, refurbished, reused. We take all of that into account, but inevitably, a lot of it's going to end up in landfill, maybe incineration, all of that included. What is also included, and is very important, is all of the emissions, all of what comes out of the system across every single life cycle phase. And classically, yes, we think about emissions as what I have pictured here, something coming out of a smokestack. But just as we don't only extract from the earth, but we also extract from the air and the water, we also emit, not just to the air, but also to the water and to the land. And so all of those extractions and all of those emissions and all of the associated burdens get summed up into the potential to cause environmental impacts. We classically think of these as greenhouse gas emissions, energy demand. We also talk about blue water consumption. Blue water is water that could be potable as opposed to gray water. Consumption is different from water use, which is a gross. So water use is total withdrawals. We talk about water consumption. That's all of the water that's withdrawn, less any water that could be reused or recaptured within the ecosystem. And there are many, many other environmental impacts, but those are the three that we're going to talk about the most here. So now that you all are LCA experts, I'm going to talk specifically about how we did this study. If you are familiar at all with LCA, you know that the functional unit is incredibly important. It's the basis upon which you present all results for a life cycle assessment. And it's really important that your functional unit represents both a function and is a unit. I know this sounds really simple, but trust me, it can get really challenging to identify a function and a unit when your system does a lot of things and has a lot of units. Right? So it was very important and very challenging in this study to identify what that functional unit would be. So the one that we came up with is virtual cores, or VCs, you'll see that. So it's the smallest operational unit of a given amount of memory and processing capacity. So it's the basic unit for the cloud ecosystem. You could squabble, you could say, oh, maybe we should have a different unit, but this is the one that we came up with, and this is what all of the environmental impacts that we quantified will be presented at. So greenhouse gas emissions per virtual core, primary energy demand per virtual core, blue water consumption per virtual core. Now, I talked a little bit about how we in LCA ideally do cradle to grave. Yes, you can do cradle to gate as well, but we did cradle to grave. So that's all the raw material production. We took into account the building, the raw materials that it takes to make the servers, the racks, when we looked at the liquid cooling, the tanks, the cold plates, everything. All the raw materials of production, all of the use phase energy, the direct energy to power the servers, the overhead for any type of cooling. There were some things excluded, you know, office space and that sort of thing, but anything directly involved in the operation of the data center was included. And we also looked at end of life. And that also plays into lifetime, the lifetime of the data center. We looked at how many replacements have to happen of the hardware. How does different cooling technology affect how often you have to replace these things? So different cooling technologies extend the lifetime of different pieces of hardware. All taken into account, including looking at refurbishment of the hardware once it's taken out of the data center and goes on to some second life. So it's pretty comprehensive what we did, and it took us a very long time. And finally, just to give a little more explanation around the function of the unit, because it is really important. When we talk about a virtual core, we're taking into account the energy provided by either the grid, but we also looked at a renewable energy scenario because Microsoft is committed to 100% renewable energy at all of its data centers globally. The data center itself, the building, you might be thinking, how do you get a building down to a virtual core? Well, you take into account its lifetime, amortize that, all the way down to what it takes to provision that individual core. The server, yes, it includes everything, the DIMMs, the flash, the CPU, the HDDs, all of that across the entire data center, and the SW stack as well in terms of calculating the workload required to provide one virtual core. So that's a lot I crammed in there, but I'm going to hand it over to Teresa Nick to talk about our results.
Thank you, Julie. Hi, everyone. I'm Teresa Nick, Director of Natural Systems and Sustainability on the Systems Technology team at Microsoft. Getting to the results of this LCA, what were the predicted impacts of 4 different cooling types in the same hypothetical data center? So here we're showing GHG emissions when the data center is running on grid electricity. The y-axis is the GHG emissions normalized to the overall maximum, which was for air cooling. Overall, the three liquid cooling technologies had lower greenhouse gas emissions with an average of 17% decrease. Note that the cold plate and the one-phase immersion are on par with the two-phase immersion here. The other thing I'd like to highlight is that the use phase electricity for servers dominated the impacts, so the blue there that you see, followed by use phase electricity for data center support equipment and embodied impacts of the servers. So that was GHG emissions. Moving on to blue water consumption. Again, we see the pattern where all 3 cooling technologies have lower impacts than air cooling. And again, we see that server use phase electricity, the blue, the navy there, the lighter blue that you see is the server use phase electricity. I'd like to point out that the lion's share of use phase water consumption was for electricity generation, not water usage for cooling the data center. So now I'd like to shift gears a little and compare greenhouse gas emissions with grid electricity versus renewable energy using just air cooling as the example. So using renewable energy significantly reduces total emissions by 89%. That's not what I'm showing here. Here I'd like to highlight the different life cycle contributors to each. We've normalized each column's breakdown to its own maximum to highlight the different contributors. What we find is that the major sources of emission changes when we switch from grid to renewable energy. For grid electricity, server use phase dominates, as I showed in previous slides. In contrast, when we switch to renewable energy, the embodied carbon of servers becomes the main contributor, followed by server use phase electricity, which moves to second place, and then embodied carbon in the data center building. And again, that was greenhouse gas emissions, now shifting to blue water consumption and making that same comparison between grid and 100% renewable energy. renewable energy did reduce the blue water consumption by 55%, but here I'm showing normalized to maximum to highlight the ranking of the various life cycle contributors to blue water consumption. I'm showing, in contrast to GHG emissions, shifting to renewable energy did not shift the ranking of the main contributors to blue water consumption. This is because water is used for solar panel and other manufacturing, as well as hydroelectric renewable energy generation. Now I'd like to go over some of the main conclusions and recommendations of the study. So conclusions with regards to data. Information on embodied impacts of data center equipment is hard to find. Specifically, there aren't enough public environmental product declarations or EPDs and life cycle assessments. Also, what data sets and tools that you use impact the results. So it's really important to get the highest quality, reputable data sets that you can. Talking about conclusions on the cooling technologies, all liquid cooling technologies reduced impacts relative to air cooling. This LCA comparing air and liquid cooled data centers demonstrates that liquid cooling has excellent potential for reducing environmental impacts. Specifically, GHG emissions were reduced by an average of 17%, energy by an average of 17%, and water was reduced by an average of 41%. Now on to the recommendations. With regard to life cycle assessments, use LCA during design to predict impacts and guide the changes that you're trying to enable. To share data and encourage suppliers to provide EPDs. It would also be recommended to integrate LCAs into engineering processes and roadmaps. And we recommend that OCP drives alignment on functional units for data center lifecycle assessments. With regard to cooling, our recommendations are that the community would work together to drive liquid cooling technology development, as is evidenced in this meeting, and also to test different designs, technologies, scenarios, and parameters to evaluate the trade-offs. We have several calls to action for us as the OCP community. Join the OCP sustainability work streams. Learn how to run LCAs at data centers from the Alissa, Sinistore, and Leo OCP white paper guidelines LCA for cloud providers. We also call the community to run LCAs for cooling and other innovations. We should publish the findings and share data, and we should also share tools. And note that we do plan to share, as Husam mentioned, the tool used to calculate the results that we've just shared later this year with the OCP community and beyond. We encourage suppliers to share environmental product declarations or EPDs. And we encourage discussion and risk mitigation of the various trade-offs of different cooling technologies. Thank you.